Today we will be talking about the group 13 elements of the periodic table. Elements in this group are primarily metallic, consisting of 4 metals: aluminum, gallium, indium, and thallium, and 1 nonmetal, boron. In contrast to groups 1 and 2, the group 13 elements show no consistent trends in electron affinities, melting points, and electrottivities, whereas the ionization energies, boiling points, and electron affinities and atomic size do generally follow some sort of trend. Some of these anomalies can be explained by the increase in effective nuclear charge that results from poor shielding of the nuclear charge by the filled D and F subshells, such as the ionization energies of indium and thallium. Other characteristics, such as density and metallic character, do in fact follow a consistent trend. Ionization energy is the energy required to remove an electron from an atom. The ionization energy generally decreases moving down the group. However, thallium has the second highest ionization energy. This is due to the lack of shielding from the 4f and 5d electrons, and so the valence electron is held tighter to the nucleus. Electron affinity is the change in energy of a species in the gas phase when an electron is added, or rather, the likelihood of gaining an electron. As seen from the table, the electron affinity does not follow any particular trend, where aluminum has the highest electron affinity, gallium and indium have the same electron affinities, and thallium has the smallest electron affinity. The melting points generally decrease moving down the group from boron to gallium, but then there is an increase as you continue to move down the group from gallium to thallium. Contrary to the melting points, the boiling points follow a trend where they all decrease as you move down the group from boron down to thallium. Electronegativity is the ability of an atom to attract electrons in a chemical bond. Boron has the highest electronegativity while the rest do not follow any particular pattern, where thallium is the second most electronegative and aluminum is the least electronegative. The general atomic size trend is increasing as you move down the group. However, gallium has a smaller atomic radius than aluminum. Gallium is significantly smaller than expected from its position within the group 13 elements. The rationale for this may be attributed to an analogous effect as seen in the lanthanide contraction observed for lanthanides and the third row of transition elements. In multi-electron atoms, the decrease in radius brought about an increase in nuclear charge is partially offset by increasing electrostatic repulsion among electrons. In particular, a shielding effect results when electrons are added in outer shells. Electrons are already present and shield outer electrons from nuclear charge, making them experience a lower effective nuclear charge on the nucleus. The shielding effect exerted by inner electrons decreases in the orders s, p, d, and f. As a subshell is filled in a period, the atomic radius decreases. This effect is particularly pronounced in the case of lanthanides, as the 4f subshell is not very effective at shielding the outer shell, that is, n equals 5 and n equals 6 electrons. However, a similar but smaller effect is observed in gallium, thus explaining why it has a smaller atomic radius than aluminum. The metallic character and densities, as mentioned before, follow a consistent trend, where the metallic character increases as you move down the group from boron down to thallium. The same is true with the density, where the density increases as you move down the group. As far as the relation between other elements with group 13, it is important to note that boron behaves differently from the rest of the group, and thus it needs to be discussed separately. As mentioned before, the other elements in the group exhibit more typical metallic behavior as you move down the group. Chemically, boron is a nonmetal in its tendency to form covalent bonds. It shares more similarities with carbon and silicon than with aluminum and other group 13 elements. Like carbon, boron forms many hydrides. Like silicon, it forms oxygen-containing minerals with complex structures, also known as borates. Compounds of boron have been used in the preparation of glazes and borosilicate glasses. but the element itself has proven extremely difficult to purify. In boron hydrides, called boranes, hydrogen often serves as a bridge between boron atoms, a function rarely performed by hydrogen and carbon chemistry. One way to address this is to consider the bonding of diborane. Diborane has 12 valence electrons by the Lewis approach. 8 of these electrons are involved in bonding to the terminal hydrogens. Thus, 4 electrons remain to account for the bonding in the bridges. This type of bonding involving 3 atoms and 2 bonding electrons per bridge, as described as 3-center, 2-electron bonding. Another interesting parallel between boron and carbon chemistry is offered by boron nitride. Like carbon, boron nitride exists in a diamond-like form and in a form similar to graphite. In the diamond-like or cubic form of each nitrogen is coordinated tetrahedrally by 4 borons, and each boron by 4 nitrogens. As in diamond, such coordination gives high rigidity to the structure and makes boron nitride comparable to diamond in hardness. In the graphite-like hexagonal form, boron nitride also occurs in extended fuse ring systems. However, there is much less delocalization of pi electrons in this form, and unlike graphite, hexagonal boron nitride is an insulator. As in the case of diamond, the harder, more dense form, or the cubic form, can be formed by the less dense form under high pressure.
The boron family, from boron to thallium, exhibit an array of traits that underline their behavior in the context of inorganic chemistry. First of which to be explored would be this group's chemical properties and reactivity. Boron is a key example of a Lewis acid. The fact that boron is electron deficient, it is compelled and drives the exception of electron pairs. Other elements in the group, such as gallium and aluminum, maintain similar properties, however, to differing extents. The exception of these electrons form complexes with varying Lewis bases, which is key to numerous catalytic processes. The boron family also acts as reducing agents. This common thread among the elements in this group describes the electron donating behavior that is specifically well known for boron, making group 13 properties pivotal for varying redox reactions. Compounds formed through this group are characterized with their considerably high energy for dissociation, attributing to their overall stability the behavior within chemical environments. Seeking stability, elements such as aluminum and gallium tend to form 3+ ions via shedding their outer electrons. The inert pair effect is most notable in heavier elements such as thallium, highlighting the differing oxidation states between the lighter and heavier elements. The inert pair effect tends to decrease the stability of higher oxidation states, due to the higher oxidation state requiring an increase in participation in s electrons. As a result, the lower oxidation states typically become more stable. Now transitioning to the compounds and reactions that feature the significance of group 13. There is an array of compounds that boron forms, such as boranes and borates. The borates are characterized with their complex structure and reactivity that is typically the most useful for organic synthesis, while borates tend to be more key in material sciences and pharmaceuticals, as they are often used as acting stabilizers. Aluminum-boron bridge molecules reveal the capability of complex and intricate bonding patterns and structure. Typically exhibiting ionic and covalent character throughout, the bridges tend to influence the overall stability and properties these molecules possess, typically impacting their reactivity in different chemical environments. The formation of metal oxides within this group play a pivotal role in varying industries to serve as catalysts and uses in semiconductors and varying photocatalysis reactions. And finally, The amphoteric behavior exhibited specifically by aluminum and gallium truly brings to light the duality of all of these elements being able to act as acids or bases.
So here we have some practical applications and uses of our group 13 elements. First, since boron is very durable, it's useful in many different materials like fiberglass. It's also used in ceramics to make them more heat and scratch resistant. And then lastly, since it can withstand such high temperatures, it's useful in kitchenware like pots and pans. And then aluminum, of course, we use in the canning of food. We make aluminum metal cans because aluminum is both relatively lightweight and it is resistant to corrosion. When we discussed aluminum's reactivity, we mentioned how it makes these metal oxides. So when exposed to oxygen, aluminum oxide will form and create a thin layer over the surface of the metal, which then protects the can from any corrosion and damage. Lastly, gallium and indium are used in both LEDs and solar cells. So solar cells convert light into electricity, and LEDs use a semiconductor heterojunction diode. And adding gallium or indium will create a p-typed doped semiconductor, and then the heterojunction is made by doping semiconductors with both the group 13 and group 15 elements, and this improves the conductivity and creates the light emittance of LEDs. For our interesting fact, we have that gallium can be used in cancer treatment. We found this research article that uses this gallium molecule shown here on the right in anti-cancer drugs. These molecules can be used in the fluorescent imaging of tumors, and they are also phototoxic to cancer cells. So after being activated by light illumination, they will form reactive oxygen species, which then react and destroy the mitochondrial membrane of cancer cells and result in cell apoptosis. And phototherapy with these molecules is beneficial compared to other methods like chemo and radiotherapy because it is minimally invasive and the treatment area can be finely selected and controlled with the activation of light, so it has low toxicity with any normal healthy cells. And these are our references with all of the sources that we used, and that concludes our presentation. Thank you.